Okay, so in the next few lectures, I want to at least start talking about inductive logic. Unfortunately, given the way the semesters went, with having to go to the online format and missing a week of classes, we're not going to get as deeply into this as I would have really liked. But I do think it's really interesting and honestly really important to say a little bit about inductive logic. And, I guess the interesting part, we'll see. Maybe you won't find it as interesting as I do. Hopefully you do. Um, but I mean, the important part comes to this that we're often really bad with inductive logic. Deductive logic, we don't always. People do make mistakes. They're not always sure about things. It can be complicated. But they don't tend to make the kind of howler mistakes with deductive logic that they do inductive logic. People make really silly mistakes with inductive logic all the time. Or maybe I shouldn't say they're silly, because I tend to make them too, or at least I did before I really started to delve into this stuff. So we talked about a few last time. The Monty Hall problem, which did not seem intuitive. Hopefully it does seem intuitive to you guys now. And also this one about the medical test, which I was rather surprised and impressed y'all actually got correct. But a lot of people messed that one up too. They actually did a version, I think it was a little trickier than the one I did, and it involved a cancer test, and they gave it to doctors, and I think something like only 20%, a little over 20% of the doctors got it right. So interesting, but also scary, and if doctors are messing this stuff up, you guys can hopefully see why it's important. All right. So today I'm just going to talk about a few basic rules, but I think to get into these basic rules, it's interesting to take a case. And this is actually taken from a questionnaire that these two psychologists, Kahneman and Tversky, gave. You guys might have heard of them. If you haven't, if you take any psychology classes or even maybe some economics classes, I'm betting you will. These guys are justly famous. I stole this example from Ian Hacking's Inductive Logic book. Also a very good book, a little more technical than the Weisberg, but, if you guys like this stuff, not a bad book to look into. All right. So here is a little story that Kahneman and Tversky gave their subjects, and then they asked them some questions about it. So let me give you guys the story. Pia is 31 years old, single, outspoken, and smart. She was a philosophy major. When a student, she was an ardent supporter of Native American rights. And she picketed a department store that had no facilities for nursing mothers. Rank the following statements in order of probability from the least probable to the most probable. So, having heard this little story about her, take these statements, which are the most likely, which are the least likely. So, A, Pia is an active feminist. B, Pia is a bank teller. C, Pia works in a small bookstore. D, Pia is a bank teller and an active feminist. E, Pia is a bank teller and an active feminist who takes yoga classes. F, Pia works in a small bookstore and is an active feminist who takes yoga classes. So just think about this. I'll give you guys, maybe 10 seconds before I move on. Just think about this. How would you rank these? Look at them, think, you don't even have to write down a piece of paper, but just roughly, what order would you give these statements if you were trying to say, well, what's the most likely here down to the least likely, right? All right. Think about it just another second. I don't want you to think your audio's busted on this. Just want to give you a little time to think about this. All right. So I'm going to tip my hand a little bit here. There's no objectively right exact ordering of these. I don't know if A is more likely than C or, whatever. But there is a rough ordering. So what is that rough ordering? Well, we can argue about how to order the statements A through C, and we can argue about how to order the statements D through F, but A through C, active feminist bank teller works in a small bookstore, have to come before D through F. We don't need to know anything about PO or how many bank tellers or, bookstore workers there are in the world to know that A through C are more likely than D through F. Why is that? Why don't you need to know anything about the probability of these statements to know that A through C must be more likely than D through F? Now, the interesting thing here is some of you guys might have said F was the most likely. I'm not sure how many. This was actually the result in Kahneman and Tversky's research. Most of their studies said F was more likely than A, B, or C. In fact, it isn't. It can't be. But why not? Well, think about the logic of these statements. Now, the logic of these statements looks like this. You guys will notice this looks rather familiar from what we've been doing with, symbolic logic in deductive logic, right? We have letters, and then we have our little and symbol, right? The one thing that's unfamiliar here is this PR. That just stands for probability. But look, if you were symbolizing, or the probability, if your question was, well, how probable are A through C? You could say probability F, probability T, probability B, right? Probability she's an active feminist, probability she's a bank teller, probability she works in a small bookstore. Now notice the logic of D through F though, right? D is the probability of T and F. E is the probability of T and F and Y. F, probability of B and F and Y. This is using this very familiar conjunction that we've talked about, right? And think about this, right? When you have a conjunction, is that more likely to be, when you look at a conjunction, is it easier for a conjunction to be true, or is it easier for the two statements that make it up to be true, right? Well, in deductive logic, it's much harder for the conjunction A and B to be true than it is for A or B, right? If A is true, then A is true, right? But for A and B to be true, both A and B have to be true. It's much more demanding. Whenever you see the conjunction sign, you guys might have gotten into the habit of thinking, well, A and B, that's more demanding than just A or B on its own, right? There are less lines on the truth table, that are true. The same holds for inductive logic. A conjunction of, B and F and Y is way less likely to be true than B on its own. It's way more likely that she just works in a bookstore than it is that she works in a bookstore, is an active feminist, and also takes yoga, right? Now look, we'll talk about this in a second. For inductive logic, you aren't going to be able to give these, neat true or false statements, but the same sort of logic holds, right? The conjunction is more demanding, therefore less likely to be true than is any of its parts, right? T is more likely to be true than is T and F. This isn't in Kahneman and Tversky's study, but I think it's also worth thinking about. Which of these is more likely? Pia is an active feminist. She's an active feminist, or she works for a large bank. She's an active feminist, or she works for a large bank, or she votes straight down the ticket Republican. Now, again, which of these is least likely and which of these is most likely? Thinking about even our little story we had about her to begin with. Well, again, this is one of those questions that kind of inclines you in the wrong way. But again, C, this is kind of opposite of what you might think. C is the most likely to be true. A is the least likely to be true. Why? Well, again, think about the symbols. This is a case of disjunction, right? First one is just the probability that F. The second one is the probability that F or B. And the third one is F or B or R. And think about it. Disjunction is in a sense opposite of conjunction because, when you add a statement with disjunction, F or B is much less demanding than is F, right? F is only true if F is true. F or B is true when F is true or when B is true, right? Way more circumstances when F or B is true than there are circumstances where F is true, right? You add even more stuff on with the disjunction symbol, it gets even easier for the statement to be true. F or B or R, there's a lot more, if you think back to the truth table, there's a lot more lines where this statement is true than there is where any of these statements are true, right? Same thing with inductive logic. F or B is always going to be more, is never going to be less likely than F. Usually it'll be more likely, but at the very least it'll never be less likely. F or B or R is never going to be less likely than F or B. Usually it will be more likely. We'll talk about that in a second. We'll talk about some basic rules here. But you guys, I hope you can see, the basic logic, there's going to be some differences with inductive logic, but the basic logic tracks, right? Conjunction, more demanding. Disjunction, less demanding. All right, so a couple more things I want to say about inductive logic with this stuff on the table, just to introduce it. In inductive logic, we will use most of the same symbols that we've used for symbolic logic in deductive logic. We will use letters. We'll symbolize our statements with a letter. Usually we're not going to use this sort of one with a variable in a statement because these aren't trying to cover all of something. They're just covering one specific case, right? We will use the letters, though, to stand for a statement. And we'll use symbols to go along with those letters to build larger statements involving more than one statement. Now, of the symbols we've looked at, we're going to use 3 of them in inductive logic. We'll use the little negation symbol, we will use the conjunction, the and symbol, and we'll use the little v for disjunction. The arrow symbol for if-then and the sort of double-headed arrow symbol for biconditionals, those will not pop up in inductive logic. We have another statement, another little symbol for conditional probability we might or might not get to, but the conditional symbols you use in inductive logic are just not going to pop up here. Okay, so a couple more points just to finish up. So one thing is, how do we define statements in inductive logic? In deductive logic, we always had these truth tables. That's how we define like our little symbols, the or, the not, whatever. Well, how are we going to define them in inductive logic? One thing you can't do, you can't just assign a T or an F, right? Inductive logic, deductive logic doesn't deal in probabilities, so it's going to go with true or false. It's very much binary, right? Inductive logic talks about probabilities. So what we'll do to define a statement in inductive logic is to assign or give a probability to it. You guys don't need to freak out too much. We'll add, it's going to be a little adding and multiplying fractions, but it's not hard, right? So for each letter and then the larger statements built up with them, you're going to assign a probability. Don't, deductive logic, very much binary. It's all 1 or 0. Every now and then you'll see a 1 or 0 in inductive logic, but usually it'll be some fraction between them, right? And that is how you define the statements in inductive logic. So I'll give you guys an example. So what's the probability, imagine I flip a coin twice. What's the probability that at least it'll come up tails once and heads once, right? Not thinking in the order, just like we get 1 heads and 1 tails. Well, it's 1/2, right? If you guys don't believe me, you can work this out. But the probability that statement is true is 1/2. What is the probability that when you flip a coin twice, you get tails or heads? Well, it's 1, right? There's no way that you're not going to get at least one of these. Sometimes things will be 1. They can't be. Usually they'll be somewhere between 0 and 1, though. Okay, hopefully that makes sense. For deductive logic, it's all, in a sense, 0 or 1. It's either true, definitely, or it's definitely not true. Inductive logic admits a lot of stuff in between. Okay. So I know this is all very fun, right? Talking about rules. So let me just give you guys a few very basic rules of inductive logic. I'll give you guys a few more. I'll have to see how far we get into this, but I do want to get a few down. So any statement in inductive logic has a value between 0 and 1. So can be as low as 0, but no less, can be as high as 1, no greater, right? Think about this in percentages. That's the way a lot of times we'll talk about probabilities, 0% to 100%. Some other ones, the probability that A is always greater or equal to than the probability of A and B. This was when I was talking about the statements with, our little bank teller, fiction, that's what I was trying to get at, right? Any of these statements that have a conjunction going to be less likely than the letters that make up the conjunction. Or at the very least, no more likely. Usually less likely, and even in extreme cases, it'll just be equally so. Another very basic rule of inductive logic, the probability of A or B is always greater than or equal to A. Remember, when we add this or, the statement gets easier to satisfy. So A or B, at worst, at worst it's equally probable to A, even if B has 0% chance, and usually it'll be somewhat more, right? Probability that A or B is also greater than B, right? So hopefully that all makes sense when you think about the logic of, conjunction and the logic of disjunction. Slightly new stuff, but this does, I think, fit with the stuff we've done with deductive logic, even if we are taking it in slightly different directions.